Okay, everybody, there'll be 12 videos coming out this week, 10 on the topic of countability. We're going to work our way up there. The main topic this week is countability, but we'll work our way up there, starting in video 1 of 10 on the topic of countability, where we'll just be talking about relations and tuples. So we've already talked about relations and tuples in IndProp, where we defined relations using inductive propositions. This isn't exactly how math folks tend to do it. They tend to think of a relation in a slightly different way. Ooh, boy. Not a good day for computers for me. Relations in math are really the same thing as sets of tuples. Okay, so let's think about a couple of examples of this. Just intuitively to get a feel for what we mean by this. So we could define a relation. Ooh, I really don't. I'd prefer it if you wouldn't move. Runs from. That's going to relate trains to pairs of stations. Okay, so how do you give the type of a relation in math? Well, the idea is if a relation is a set of tuples, the type of a relation names all of the tuples that could be in there. So, for example, we'll say runs from is a relation that's a subset of train times station times station. So a tuple will be a triple, a three here, a thing, three entry thing of a train, a source station, and a target station. Though trains typically go two ways. Now we could think of the runs from relation where every train goes from every station to every station. That won't be the case. We just give the type here, right? This is the type by saying that we're a subset of that type. Okay, let's think of some concrete examples. So in LA, the San Bernardino, the SB train, runs from Claremont to Union Station. Not in downtown LA, not to be confused with, say, Union Station in DC. This is a tuple that's in the runs from relation. Okay, similarly, San Bernardino says there's a train that runs from Montclair to, I don't know, El Monte. There's another station on that line. Also in runs from. Oops. Okay, let's look at another. The Riverside train goes from downtown Pomona to, I think it goes to Union Station. I know it goes to Riverside, so let's do that one. Okay, but there does not exist a train T such that T runs from Claremont all the way to, I don't know, a beach. Anywhere interesting, anywhere you'd want to go. Let's say to downtown Pomona. Okay, so we've just been using right here the notation from sets. Right here, this is set. Oops, that's the wrong. Set membership to talk about membership in the relation. You can give a different way of writing it, where we would say SB runs from Claremont to Union Station, where these parts I've just highlighted are sort of syntax, right, for a three-place relation, which is a little cleaner than writing the tuples, though they're sort of interchangeable. So when you define a relation, you want to sort of set up what you mean by that. Okay, so this was example. Oh, nope. This was, come on. Example 1. Let's look at another example. So this will be another three-place relation. Blank recorded blank in blank is a subset of musician times album times year. Okay, so what's in this relation? I'm just going to use what I've done over here is I've given the three-way relation. What I mean to say is I've given the three-place syntax. So what I can just say is something like, okay, David, why does it keep changing back? Oy, I'm sorry about these technical difficulties. No computer has done what I wanted it to all day. Sometimes you just have that day. David Bowie recorded Hunky Dory, probably his best album. I mean, this is open to disagreement. I think there's a lot of different things going on here. But Hunky Dory is the first truly Bowie album. I really recommend it very highly. In 1971. Okay, cool. Paul Chambers, probably the greatest bassist ever to have lived. Again, that may be open to disagreement, but I really doubt it. If you disagree, please let me know about it on Piazza. He recorded Bass on Top. In what year was it? 1957. That's right. Okay, cool. One more. I'll do it in tuple notation this time. Public Enemy. It takes a nation. Gotta spell that correctly. Whoop, let's just rewrite that. Of millions to hold us back. Okay, now here there's a tricky part, right? It was actually recorded in 1987, even though it came out in 1988. So this is in, call it the RI relation, recorded in. So just a quick note there is like, okay, you have to know what the bits of your relation mean when you're defining a relation. Like here we're talking about the year it was recorded and not the year it came out. Right? Critical stuff. Okay, and so then we could write other interesting things. So there exists a unique R Y such that Prof. Greenberg R Y is in that relation. Okay, there exists R1, R2, Y1, Y2 such that Prof. Chandler, some of you may know him in the math department, R1, Y1 is in RI, and then also R2, Y2 is in RI, and then just to be clear, R1 does not equal R2, Y1 does not equal Y2. Okay, so these are logical facts that we could say about this RI relation that also both happen to be true if you're into that sort of thing. Okay, these are sort of, I think, hopefully really relatable non-mathematical relations we've looked at so far. Let's look at some more mathy relations. Oy. Okay, so let's look at the less than relation. So we've defined less than so far, something like this, less than or equal to. So we'd said n is less than or equal to n. And we've said n is less than or equal to s of m when n is less than or equal to m. Right? So we could say that this defines a relation, right, if we like, that less than or equal to blank less than or equal to. So that, all told, is a relation on pairs of natural numbers. So we could also call this LE. Right, so for example, what this says, the first thing is that we could say this all as two rules. One, n is in LE for all n. Two, if nm is in LE, then n s of m is in LE for all n m. So what I've just done is I've taken the inference rules here and I've just translated them to mathy. That's actually totally legible, even though the rainbow is pretty blinged out. I'm going to write it in a font you can see, right? So this here I've translated to mathy notation. Okay, that's all so illegible. Let's just erase all that. Okay, cool. So then we might say that, for example, 573 is in LE. We might say that 0, 0 is in LE, but it's not the case. 2, 1 is not in LE. Okay. Cool. Let's look at a couple more examples. So here's a relation. TT is going to be this. Okay, here's our relation TT. What type is TT? Okay, well, TT, it seems to be relating one Boolean and another. Right, that's what we have in each case. So TT, if we wanted to write its type, is a relation on bool times bool. Okay, I've called it TT because it's in a certain sense a truer than relation, right? It's kind of like less than or equal to on Booleans, right? It's reflexive. We'll talk about all these relational properties in a later video, but everything's related to itself. But then also false is in some sense, less than T. So T is truer than false. Okay. Though really a better name would be less true than, right, if we're reading it from left to right. In any case, that's the truer than relation. Okay, I want to make one final remark on some other relations about unary relations. Right, unary relations are sort of a funny special case, right? So we've seen some ternary relations, that was e.g.'s 1 through 3, and then two binary relations, relations 1 through 2, and two binary relations on 3 and 4. A unary relation is a relation on one thing. So, like, what is a tuple of one thing? It doesn't really make any sense. So we think of unary relations really just as sets, right? So let's look at 2. So the first one is even, right? We've actually defined that already. EV is just a subset of n. We identify a subset of the natural numbers which satisfy the EV predicate. So we gave rules for that such that 0 is an EV, 2 is in EV, but 73 is not in EV. Okay, here's another one. It'll be the last for this video. Cannot lie is a subset of people. Right, so we're going to identify, excuse me, I wrote the wrong symbol. Is a subset of people. So it's a unary relation, which are just the same thing as subsets. So, like, who's in this set cannot lie? Well, I can think of two prominent people. The first is George Washington. He's in the set cannot lie, very famously. Cherry tree murderer. And then the other person I think that people really know who cannot lie is Sir Mix-a-Lot. Right, he's tried to lie, but he cannot. So he is also in that set of people who cannot lie. Okay, hopefully this is a clear enough overview of all of the different ways people talk about relations in plain math. We've got 9 more videos on the topic coming at you. You'll probably want to watch them in order and maybe do a little bit of bouncing around. Okay, hope everybody's doing well.